have is the Butterfly Nebula, NGC 6302, which in fact is not the Butterfly Nebula. It is the Bug Nebula. However, in our press release of this image, we said it resembled a butterfly. The internet took it over, the media took it over. It is now the Butterfly Nebula, okay? Fun fact of that. You will not learn that fact on the back of the lithograph. Instead, you'll learn other things about what this object really is, the depth of this star here, and the amazing temperature that's heating the gas flowing away from it. All right. For those of you on the internet, you can see the URL down here at the bottom. AmazingSpace.org, resource page number 59. This is one of our earlier ones on this, okay? So you can download it there. While you are looking at your lithograph or downloading it, please silence your electronics. Our AV folks have pointed out to me that I have been lax to join the 20th century and ask my audience to please quiet their phones, silence your cell phones. Sorry I don't have one of those big crazy M&M commercials that they do at the movies. Maybe I'll have to pirate one of those for next month. Okay. All right. Tonight we have Recycle Your Used Pulsars, explaining the extra gamma radiation from the central Milky Way. And how many of you looked at this and said, I have no idea what that is, but it sounds real cool. Well, this man down here is going to explain all about it. That's Christopher Britt. Upcoming on July 2nd, the Art and Science of Astronomical Image Processing from Joe DePasquale, our senior image processor here. In August, we have the exciting topic of TBA. I talked to Trisha, and she said, well, I've got two really good topics on it, and she wasn't ready to commit to any one of them. I said, just choose one. And she said, well, I'll let you know. She didn't let me know, so she's TBA. And Brandon Lawton on September 3rd, he's also in the same situation. He and I discussed today, and he going, well, he also has two topics that he wants to talk about. Maybe I have to twist some arms to get some names, some titles, but at least you know we have speakers for August and September. If you want to see their titles, you can find this webpage about our upcoming lectures over here on the right. The links to our webcasting here on the left. You can watch the past lectures on YouTube and in the STSCI webcast all the way back to 2005. So, wow, that's 14 years worth of universal cosmic knowledge. Ooh, baby. If you want to sign up for email, this is the easiest way to do it right here. Enter your email. You can also unsubscribe. Okay, although why would you want to do that? As for those announcements, you can sign, if you don't like to sign up the website, you can just write your email address on a piece of paper, hand it to me by the old-fashioned paper method, and I will make sure you get signed up. If you have comments and questions, you can send them to publiclecture@stsci.edu. For those of you who like to follow social media, we have a variety of accounts on Facebook, Twitter, YouTube, and Instagram, not only for Hubble, not only for the James Webb Space Telescope, but also for our institute, the Space Telescope Science Institute. Myself, I do a little bit of social media on Facebook and Twitter. And tonight, the observatory has said they are going to be open. Did anybody look up? Was it clear when we came in? Yeah. Yes. All right. So we are looking good for the American Space Grant Observatory being open. If you can't do it, if at the end of the lecture you want to go across and look through the telescope, we'll meet down here on the right at the end. If I forget, somebody remind me, or Irini, if she's here, will probably slap me and say, "Wake up, Frank." And if you do not get to do it tonight, or you can't do it tonight and want to do it some other time, they have open houses on Friday evenings. Go to md.spacegrant.org. Now, our news from the universe for June 2019. Our first story, lopsided star formation in NGC 4485. Ah, yes, 4485. I remember it well. Of course, I have no idea what it is. But first thing, we got to talk about normal star formation, okay? So this is a very famous galaxy, Messier 51, also called the Whirlpool Galaxy. And you can see it's got this beautiful symmetric spiral pattern, okay? Call this a grand design spiral. One of the really striking features of this image is all of those red dots around it. So you see all these red star-forming regions that swirl around along the spiral arms. These are the places where stars are just forming, okay? The red is hydrogen alpha, which is a hydrogen gas heated to about 3 of these star-forming regions. But you notice how they're smoothly spread out throughout this galaxy. And this is what we sort of expect because, the density waves that produce star formation just, flow throughout an entire galaxy and you see them. Well, we released an image last month of NGC 4485 and tell me what you don't see here. You don't see that same sort of symmetry, okay? You see that all of the star-forming regions are over here on the right side of this galaxy, and the left side looks kind of like non-star-forming regions, okay? Old stars and a little bit of, young blue stars. So what's going on here? What does this indicate? Anybody have a guess on this? You've got a disturbance on one side, right? Yeah?
Result of galaxy collision.
A result of galaxy collision, not quite a collision, but an interaction, okay? When you see that that star formation, that means that something funky is happening on that side and that side only. And if you take a larger view from a ground-based, this is where the Hubble image is within this larger view. All right, and this is NGC 4490 and 4485 as taken by the internet name J. Schulman 555. I couldn't actually find out what this person's name is. I'm assuming it's somebody Schulman. And here you see that 4490, which is in the center here, has the tidal tail stretching back towards 4485. So as you expected, very good intuition, there has been an interaction between these two galaxies, and this star formation here appears to be the result of it. So that the asymmetry in 4485 is that this was a normal galaxy, possibly with star formation everywhere, possibly with very little star formation, but at least it would have been somewhat symmetrical, and that the interaction sweeping past it. If we zoom in on the details of this, you can see that there are some very large star-forming entities here that are forming thousands upon thousands of stars. And this is one thing that this teaches us is that interactions between galaxies create these density waves that flow across galaxies and can produce copious amounts of star formation. When you see two galaxies interacting, you often see these large waves of star formation, and this image illustrates it here. There is no particular science result to this. This is one of what we call our pretty picture releases, where we have one of our gorgeous images from the archive and release it to the public to show off the beauty of the universe. But you can see in this one in particular how the interactions between galaxies can produce this star formation. Our second story, Mind the Gap, Part 2. All right, so let's start with our solar system. Our solar system has remarkable because all of the planets are basically in a plane, right? And that sort of suggests to us that, well, the planets formed in this disk that's encircling our sun, right? That seems very logical. And so we looked out into the universe looking for that, and we did find disks of material around other stars. This one, AU microscopy, over on the right, HD 107146. This, you can see an edge-on disk on the left, and on the right, you can see a face-on disk. And so we did discover these disks around young stars, where stars were formed. And then we got ALMA, the Atacama Large Millimeter Array, which is able to look in millimeter wavelengths and see these disks in unprecedented detail. And they saw H.L. Tari, seeing this gorgeous disk, not just the disk, but also the gaps in the disk. And this, to us, is like, oh, this is a holy grail, because this is where we expect the planets to form, in the disk with these gaps. Those gaps are going to be produced by formation of planets, either by the planets themselves sucking up the material or by gravitational resonances in it. So this, just blew us away, okay? So the story we're going to tell this week is about the star PDS 70. And this is one of the early observations of it. where you can see this big whitish bluish thing is a large disk, and this black spot in the center is where they're blocking out the light of the star, of course. And that you can see just around this black spot, there's a small little disk in here, but in between the outer disk and the inner disk, there is what they called in this thing a giant gap in the disk. All right. Whereas the outer disk is around 70 astronomical units in radius, 140 in diameter. That's a bit twice the distance of Neptune. The inner one, there seems to be at least a 30 or 40 AU gap in there. All right, and so the question is, are we going to find planets in there? Well, they did a little bit of follow-up observations, and yes, inside this outer disk and outside the inner disk, they did find an object, and this is planet PDS-70b. But this hasn't gotten the ALMA treatment yet. Then it got the ALMA treatment, and you see all this fuzziness? No, it goes away. Boom! That's ALMA for you, okay? Finds, just like, boom! See that you can see the detail in the ALMA observation of the outer disk. And if you blow it up on the right-hand side, you can see also the inner disk. You can see the spot where PDS-70b should be, but it doesn't show up in the ALMA thing. But you also see this spur here. That spur right there indicates that there might be another gravitational presence pulling on that outer disk. So, what the folks at the European Southern Observatory did was they did a targeted campaign on PDS-70, and they had to use the sophisticated computer algorithms to block the light of the star and try and pull out and enhance the planets that could be there, searching to see the details of PDS-70b and if there was anything else there. They succeeded. Here is one of the two existing images of a multi-planet observation. Two planets around the star PDS-70. There's only one other, HR 5899, which is a four-planet system. This is the second planetary system where we have two direct images, PDS-70b, PDS-70c, two planets around another star, and we can see them both. We can see the light. We can be able to pull out that faint light of those planets around that star. Now, this is, of course, scientific data. It's kind of ratty and ugly. And what do we do here so beautifully? We create cool graphics, all right? So, this is an artist's rendition of the PDS-70 system. You can see the star in the center, PDS-70. You can see the inner disk here. You have a PDS-70b at the top. You have PDS-70c here in the foreground. And you have material streaming onto them. Why is there material streaming onto them? Because this system is only 6 million years old, okay? These two planets are the Jupiter mass range from between 1 and 14 Jupiter masses, both of them, and they would still be forming. Jupiter mass planets take about 10 million years to form, so material is streaming onto it. This is what they believe is happening in PDS-70, is that these two planets have cleared out this gap, right? I showed you that HL Tauri image, and I said maybe planets are forming in there. In PDS-70, we know there are planets that have formed inside that gap. So I did a news story called Mind the Gap the 4, but this is Mind the Gap Part 2 because we have two planets forming inside a gap in the PDS-70 system. Our knowledge of extrasolar planetary systems is truly developing. This is a really great time to be studying astronomy because we're learning so much about what solar systems are like elsewhere in the universe. Kind of fun. All right. Any questions before I move on? Yeah.
When will solar winds blow all that stuff away?
The T2. All right. So one of the things that stops the formation of a giant planet is what's called the T-Tauri wind of a star. And that usually kicks in about 10 to 15 million years after the star has started nuclear fusion. Okay? So when PDS-70 undergoes its T-Tauri wind and blows away most of the low-density material in the system, there won't be this material to fall onto these planets, so they will stop forming. Okay? Which is why, actually, we believe giant planets like Jupiter have to form in that first 10 million years, because the low density material that would normally fall onto them is gone after that. One other question before we go?
The picture before this one looked like it had another light blob down to the right.
Yeah, you're talking from PDS-70b, just a little bit to lower than that. Yeah, we recognize that you're trying to pull signal from a lot of noise, the signal to noise suppression, and if that were real, they would have trumpeted it. But obviously, the researchers who processed this image said, no, that doesn't have enough signal to noise ratio to indicate that it's real. Or they can't follow it. Usually to confirm planets, you want to follow them moving around. So you take different observations to see their motions.
So is there enough light that is there to like an absorption spectrum?
No, not yet. This is just the first observations of it. We'll be able, if people are trying and do spectra of things like this, you need a lot more light to be able to get spectra of something like this. Okay, all righty. Now our featured speaker tonight, Dr. Christopher Britt, is an astronomer here in the Office of Public Outreach at the Space Telescope Science Institute. He is new to us, having joined last August, you said? Yeah. So he is still learning the ropes and showing us all the new tricks that he learned. He did his PhD at Louisiana State, or was it Louisiana State, that's what I thought, okay. And then did postdocs at Texas Tech and Michigan State University, studying old dead stars and non-binary stars and the way stars die and do all these crazy things. Sometimes they, when stars die, they become pulsars, which is what I'll talk to you about tonight. Chris and I have gotten to know each other a little bit because he plays disc golf and I play disc golf. I think I play it a little bit more seriously than he does. But one other thing in his favor, he also brews his own beer. So he has disc golf and beer. Got to be one of my favorite people out there. Ladies and gentlemen, let us welcome Dr. Christopher Britt. Which one is source? I can't read that.
Yeah.
Oh, there it is.
Input. Yeah.
Which
What's the input?
Oh, that one there. It should be
It's beyond
one.
3.
Doesn't say. All right. That's 4. Shouldn't.
That's on 3. Did it turn off?
Uh-oh. Sorry, I must have pushed the wrong button. Save me, save me. Ladies and gentlemen, Thomas is coming down to save us. I blame this all on getting old. I'm looking down here trying to see which button says change input, and I couldn't read it. He's on 3. Did I hit one of these other buttons and make it go?
When in doubt, turn it off and on again.
It's back.
There it is.
Ladies and gentlemen, another hand for Christopher Britt.
Great, okay. Thanks for the introduction. And Frank definitely is better at disc golf than I am. We played together once and he beat me pretty soundly. So, but yeah, I wanted to talk about this kind of puzzle in current astronomy and astrophysics. It's something that's not really solved yet, in part because it involves just a lot of really cool stuff from all different parts of astronomy, and in part because it kind of gives a little bit of a window onto how science is done and how we go about solving these problems when the answer isn't immediately obvious. So I'm going to be talking about kind of extra gamma radiation coming from the center of our own galaxy, the Milky Way. And when you hear gamma radiation, a lot of you may have read some Avengers in the past and be thinking of the Hulk. Yeah, gamma radiation famously gave the Hulk his powers, right? So far, I haven't known anyone at NASA to turn giant and green and angry, but you never know. Maybe they're keeping it quiet. So when I talk about our galaxy in the Milky Way, I'm really just talking about the same thing you can go out on a dark night and see. So if you go out to a dark sky, maybe up in the mountains in western Maryland or wherever you happen to be listening at home, driving out away from the city and look up at a dark sky, you can see the Milky Way with your unaided eye. This image in particular was on a timed exposure with a camera, but your eye can still see even some of these dark clouds and stripes cutting through the dark stars. So it's really something to do. If you can have the chance to go out to a dark site and look up, you should absolutely take the time to do it. It's well worth it. But if you go and take pictures of the night sky, all over the sky around the Earth, the whole sky put together looks something like this. So this is like a globe for the sky. It's a global map of the entire night sky. You can see there's this plane of dust and stars stretching across the night sky, and that's our galaxy. That's where we live. It looks like a plane, like this flat line, because we're inside it. We're kind of sitting out on one of the spiral arms looking in. Okay? And you can see all kinds of other stuff scattered around. You can see these kind of fuzzballs down here. These are small galaxies orbiting ours, called the Magellanic Clouds. And if you're in the southern hemisphere ever, you can look up in a dark sky and see them with your naked eyes. They look like clouds in the sky. So they're called the Magellanic Clouds because Magellan was the first European to see them. So, of course, he got the name after him. Never mind the fact that people have lived in that part of the world for thousands and thousands of years and have been seeing them for thousands and thousands of years. But if we look at the night sky in other wavelengths, not just light that our eyes can see, we can see other kinds of things. So you may know that white light can be broken down into different colors, blue, green, and red. If you keep going past blue, green, and red, on the other side of red, there's a color your eyes can't see called infrared. If you look at the night sky in infrared light, it looks something like this. You can suddenly see through all of those dust clouds from before. So you can see all these kind of black dust blocking the light of the stars. When we look down in infrared, we can finally see the stars underneath. This is infrared light that's very close to what our eyes can see. It's just a little bit longer wavelength. So our instruments can see it, but our eyes can't. We can keep going into infrared and go into kind of longer and longer wavelengths, and the sky starts to look like this. You can see the blue here is the stars, and the green is some of the warm dust in our galaxy. But this is still an infrared image. It's just a little bit further into the infrared. Okay. If we keep going to even lower energies of light, even longer wavelengths, further into red, we start to crack into microwave and radio light. And that's what this image shows. Now, radio is very low energy light. And in fact, Carl Sagan said in 1980 in an episode of Cosmos that there is more energy in a snowflake falling to the ground than there is in all of the radio light that every radio telescope on Earth has ever detected, put together. Now, that was back in 1980. It was a long time ago, 40 years. Odds are pretty good that we're up to about 2 snowflakes by now. Yeah. So if we keep going the other direction, if we've gone kind of down in energy, if we go up in energy, then we can get up to X-ray light, the kind of light that your doctor will use to look at broken bones inside your body, or that your dentist will use to look at your teeth, the same kind of light. You can see now there's all these little bright sources that look like just bright stars. And these are the kinds of dead stars that I kind of cut my teeth on, that I was most interested in when I started in astronomy. Things like black holes and neutron stars, what's left over after a star dies. And if we keep going up in energy, we get up to gamma-ray light. So this is a map of all the gamma-ray light in the sky that was put together by the Fermi Gamma-ray Observatory, which is a NASA instrument that's up now. And they've been gathering gamma-ray light for about 10 years now. And you can see the same plane of our Milky Way galaxy here. You can see some bright individual objects scattered around the sky as well. Now, when I say it's high-energy light, that doesn't really quite get across how high energy this light is. It's really quite extreme. It's so extreme, right, it gave the Hulk his superpowers, right? So to try and put this into perspective, of how high energy gamma ray light is, I'm going to compare it to some temperatures. Okay? Because temperatures are something we have a better feel for. Right? So if we take something like hot lava, say, and look at the temperature of hot lava, we can associate that temperature with a particular kind of light. Okay? It's glowing, after all. We can see some light coming from it. And as we heat it up, it'll glow even more. It'll turn then yellow and then eventually white hot. So we can associate a temperature to an energy of light. So if we talk about hot lava, it might take a moment just to think about what kind of light might pair with this particular temperature. Okay? You can either pair it with microwave light, visible light, or X-ray light. Obviously, there's no grades or anything. Just take a moment to think about what you might expect, what type of light to match to this temperature. Now, I bet a lot of people are probably expecting that it's visible light because we can see it glowing. But in fact, the light that pairs best with it is infrared. So this lava is glowing most brightly in basically what's blue in this image, is where most of that light's coming out. Okay, so something even as hot lava is still coming out mostly in infrared wavelengths. If we cool down, say let's go to a nice beach day, kind of a nice day outside, pleasant, sitting in a hammock, breeze coming in. We can do the same kind of thought experiment, what kind of light pairs with that kind of temperature. Kind of think about it for a minute and make a prediction. Yeah, and it's again infrared light. So we're still in infrared. Now we're kind of moving to the green parts of that. If we keep cooling off, let's go somewhere more extreme, like the poles of Mars, say. Mars in the wintertime at the North and South Pole is extremely cold. It's so cold, it's somewhere between the temperature of dry ice and liquid nitrogen. Okay? So in fact, a lot of that white stuff that you can see on the poles is actually dry ice. It's carbon dioxide, the same gas that you breathe out every time you take a breath, frozen solid. Okay? And it's even colder than that. So this is a really quite extreme cold. So if we had to think about what kind of light might pair with that temperature, might you expect it to be kind of microwave and radio light, infrared light, or visible light? That's right, it's still infrared. So we still haven't even gotten down into the microwave and radio yet. To get down to that kind of energy, we have to keep going in temperature down to liquid helium. So now we're at 4 degrees above absolute zero, is the warmest liquid helium can be. Okay? And now we're finally at the level where we're just starting to crack into microwave and radio light, comparatively. So this is why we said, radio light's so low energy that even a snowflake falling to Earth has more energy than everything that we've seen in radio telescopes, is because it's just such a low energy light. If we go the other way and compare it to temperatures kind of going up, we can use this as a starting point, this liquid helium in a lab, and compare it to something like the surface of the sun. Right? The surface of the sun's famously a hot place, right? And that maps, I think probably obviously, to visible light, because that's what our eyes are seeing. It's so bright when you look outside, the surface of the sun. You don't want to look at it directly. But it's mostly emitting its energy at visible light. So the temperature of liquid helium compared to the temperature of the surface of the sun is about the same as the energy gap between microwave and visible light. If we can extend that kind of analogy, that's about the same ratio as the surface of the sun to the corona of the sun. How many people went to the solar eclipse in 2017? Yeah, some people in the back. Did you get to see the corona of the sun when you were there? Yeah? Great. Yeah, so that's a few million degrees is the surface of the sun. It's about 1,000 times hotter than the surface of the sun. The surface of the sun is about 1,000 times hotter than liquid helium. So these ratios are, hand-wavingly roughly equivalent. Okay? So let's keep scaling that up. Let's now compare, say if this is now emitting mostly an X-ray light, okay? We go microwave to visible, visible to X-ray. Let's keep scaling that up. And now we're comparing microwave to X-ray light, liquid helium to the corona of the sun. Okay. That's about the same ratio as the corona of the sun to this gamma ray light. So this is so high energy, it's really hard to get a grip on. Okay? But this difference between the X-ray light and these gamma rays that Fermi is emitting is just so extreme. It's about the same as the corona of the sun compared to liquid helium, scaled up again. It's a factor of 1 million times more energetic, the light coming out. Yeah, which is why it can give Hulk his superpowers, right? So what could possibly make this kind of light? Right? What could possibly have so much energy in it? This kind of unfathomably energetic light coming out. Generally, what happens when you have charged particles like electrons that are being rapidly accelerated. So some environments that can do that are things like supernova remnants. So this image here is an X-ray image of a supernova called the Crab Nebula, supernova remnant. And if you look in X-ray light at the crab, this is what you see. And you can see this motion in it, these ripples kind of coming out from the center there, and a bright central source in the middle. And what's happening is there's a remnant of the old dead star in the center there, called a neutron star. And as it's spinning around, it's giving some of its energy to the nebula around it. And you can see the motion in that nebula. It's accelerating these particles. As it accelerates those particles, they can flare in this gamma ray light. So this is a gamma ray movie over here, taken with Fermi of the Crab pulsar. And you can see when this flare goes off, it gets quite bright and then fades away again. And this is happening very close to the center of this nebula. So something's going on very close to the old dead remnant of this star that's creating this spike in very energetic light. So when we look at this all-sky map, we can find remnants of supernovae in it, things that we know about from other studies where we know other supernovae have gone off. So we can see they're mostly in the plane of our galaxy, which makes a lot of sense, right? Because that's where most of the stars in our galaxy are. Okay? So we can find supernova remnants. We can also find those old dead remnants of stars, the pulsars, spinning around. And we can see those kind of scattered through our galaxy, but mostly in that plane. Okay? They're a little bit easier to find up here and down here than they are in the middle. And I'll talk a little bit about why that is in a minute. We can find some pulsars. We can also find some really massive black holes in other galaxies, far away. Now, black holes in other galaxies are greedy. They eat all kinds of gas and dust, and they're messy eaters. And some of that gets shot out each end in these jets, these giant jets. And when one of those is pointed at us, you can see it in the gamma ray, see the gamma ray light coming in. So these are really massive engines pointing their jet right at us, and it's showing us their accelerated particles. There's also a lot of this fuzz, right? A lot of that fuzz is what's happening when you have electrons colliding with the light. And just like two billiard balls can collide and give its energy to the other billiard ball, that happens with electrons and photons and light. Light can gain energy from a fast-moving electron. So if we take all that stuff we know about and try and take it away from our map of the gamma ray light coming from the galaxy, subtract it all off, account for all the pulsars, all the supernovae that we know about, we're left with something extra at the end. It's concentrated in the center of our galaxy, takes up a couple degrees, not a big area. But we're not really sure what the cause of it is. There's this extra, super high energy radiation coming from the very center of our galaxy and the area around it. We don't really know why. There are a few ideas. One of them relies on the fact that we've now removed all of the known sources of the gamma radiation. So what if there's a type of thing that we can't see? What else can make that kind of light? If you remember Einstein's famous equation equals mc squared, right? Energy is mass times the speed of light squared. Something with mass carries energy with it, just inherently. So if we could liberate some of that mass into photons, then we could create some of this gamma ray light. And that can happen with antimatter. So if we have particles of antimatter in the galactic center, we can annihilate some regular matter and create this high-energy light. But we already removed the matter we knew about. We removed the stuff we could see. So what else is left? Well, maybe it's stuff we can't see. Things like dark matter, which kind of by definition we can't see. Right? Now, dark matter sounds like it's kind of a tooth fairy that people inject into the world because they can't explain everything. But there are really good reasons to think that dark matter exists. And there have been for some time. It started off through a totally different approach from just noticing that orbits don't work the way that we think they should in galaxies. If you look at our solar system and look at how fast planets move around, stuff close to the sun moves fast, like Mercury, right? The messenger god Mercury from Roman mythology moves very quickly. The stuff way further out, like Neptune and Pluto, moves very slowly. But if you look at galaxies and the velocity of stars, you don't see that kind of fall off. If you move away from the center of the galaxy, the stars don't go any slower. They stay the same speed. Now that suggests that there's matter that's still pulling on the star that we can't see. So that's kind of the origin of dark matter. So the structure of our galaxy then is we're living out here on this kind of outer spiral arm and the unfashionable end of a spiral galaxy, right? It's flat with us in the middle. We can see that on the sky. But surrounding us is this halo of dark matter, invisible to our eyes and to our instruments, but the influence of its gravity is not. Right? So the idea that we could maybe detect it directly is pretty tantalizing. Okay? There are some theories about what dark matter is. Some of those theories think that dark matter is a type of massive particle that interacts through the weak nuclear force, is what it's called. So they call it a weakly interacting massive particle, or a WIMP. Okay. Astronomers really love terrible, terrible acronyms, and WIMPs are one of them. But some theories of WIMP dark matter thinks that they're their own antiparticle. So if you have lots of dark matter concentrated, you would expect those particles of dark matter to run into each other, and when they do, create gamma-ray light, because E equals mc squared. So maybe the reason that we see this extra stuff is because that's where the dark matter is most concentrated, and that's where we see these particle annihilations coming from. So that's one idea. There are other ideas that don't involve invoking new kinds of matter, even matter that we have really good reason to think exists. Okay? And that's based on the fact that there are analogs of this excess in other places, and that the sky is really crowded. Okay? If we look at the galactic bulge, there are so many stars there, it's very difficult to tell them apart. This is an image that I took as part of my research when I was in grad school of a part of the galactic bulge. All of the white bits in here are stars. The black is the gap in between them. And this image was taken with a resolution about 70 times better than what your eye can see. So this is really quite a detailed image from the ground, and it's just chock full of stars. And an instrument like Fermi doesn't have the resolution to tell these stars apart any more than your eye does. So maybe there's a population of stuff blending together. Now, just to give you a sense of how crowded this is, okay, this whole thing would fit on the size of your pinky nail held a certain distance away. That's how much of the sky it takes up. Let's see if we can guess how far away you'd have to hold your pinky nail to take up that amount of the sky. I think you'd have to hold it in front of your nose, kind of out at arm's length, about 10 feet away, or about 50 feet away. What patch of the sky do you think that fits in? Okay, make your final guesses here. Yeah, it would have to be about 50 feet away. So those of you in the back of the room are about 50 feet away from me, my pinky nail would contain everything in that image. And that's tiled kind of over the center of our galaxy. So it's just chock full of stars. And some of those stars have died, and some of those stars are now pulsars. And since Fermi is relatively blurry, it's possible that those could blend together into something else. Okay. So I don't know if anybody recognizes what this is so far. No? So there's a style of art where you draw kind of large colored dots on the canvas, and when you stand far enough away, they blend together into a new image. Okay? So here we're standing kind of close enough to the painting that we can't tell what it is. It's just a bunch of colored dots. As we zoom out and things blur together, a shape starts to emerge until finally the full piece of art is revealed. So something similar could be happening with the stars in the galactic bulge, where individually, if you had the resolution, you could pull them apart into the individual colored dots. But with an instrument that has less resolution, like Fermi, they blur together into kind of the smooth-looking art. Okay. So could these gamma rays be coming from lots of small things that blend together? Okay. Well, we have examples of when this happens. This is a star cluster, okay, called Tarzan 5, and it's in our Milky Way. It's called a globular cluster. This image was taken with the Hubble Space Telescope, and you can see lots of individual stars here. Right? And if we look at that cluster in gamma rays, this is what it looks like. So you can see that it just looks like one solid blob. Okay? You can't tell the individual stars apart anymore in the gamma ray. So maybe whatever is responsible for those gamma rays in the cluster is the same kind of thing that's responsible for the gamma rays in the galactic center. Globular clusters don't have dark matter. Okay? We've kind of studied lots of them, measured the velocity of their stars moving around, and they behave like you would expect them to if all of the mass is coming from the stars. They don't seem to have any dark matter. So if the same thing is responsible for the gamma rays in the cluster as in the galactic center, then it's not dark matter, it's something else. Okay. There are these objects in these clusters, these old dead remnants of stars that can give you high energy light. This is an X-ray image taken of Tarzan 5 with the Chandra X-ray Observatory, and you can see these individual points sitting around in the core of the cluster. These are what happens when you have an old dead star feeding on something, kind of a zombie star. Right? So what happens is, as the star dies, what's left is its shrunken core, okay, called a neutron star. So to give you a kind of a quick primer on how neutron stars, how small they are, and how dense they are after they've shrunk down, we can compare it to something that maybe most of you are familiar with, the city of Baltimore. Okay? So if we put a neutron star down on top of Baltimore, see how big it's going to be, it fits pretty neatly inside the loop, okay, around the city. Okay? They're somewhere between 10 and 15 kilometers in radius. Okay? The one I've drawn here is 11 kilometers in radius. Fits pretty well. Okay? These spin around really rapidly. Most of them spin around about once a second. Take about a second to make the entire loop around Baltimore. Okay. So these also weigh more than the sun does. Just for comparison, 99.5% of all the mass in the solar system is wrapped up in the sun, and most of what's left is in Jupiter. So weighing more than the sun and fitting into something the size of Baltimore is really quite dense. If you had to guess, a teaspoon of neutron star, how much do you think that would weigh if you just dipped a little teaspoon of neutron star out? Yeah, it'd be C. Yeah, 10 million tons from one teaspoon of neutron star. Are fantastically dense. Yeah. Something interesting can happen when you get it close to another star. It can start to eat it. And that happens a lot in these globular clusters. Okay? Deep in the core, this is a really dense environment. This whole area here is about the size of the distance between the sun and the nearest star to the sun. So where we are, we'd have the sun and then Alpha Centauri, the closest star. In the same image here, we've packed hundreds of thousands of stars. So they're so close, they can really interact and have a lot of cool things going on. So this is a simulation of a way that they can interact. There's a binary up here, 2 stars orbiting each other. One's green, one's blue. And there's another one down here, another pair of stars orbiting each other. One's yellow, one's red. So keep your eye on the green one and the yellow one. These 2 pairs of stars are going to go by each other. Watch what happens to them. Now you see how close together the green one and the yellow one get at the end? Right? And how fast they end up spiraling around each other? So when they get so close together, it becomes important that something else happens to stars as they age. Stars expand as they age. So once you've gotten a neutron star and another star close together, when that star starts to age and get old, stars much, like people pass, I'm starting to get there myself, have to regulate the intake of beer, right? Start to expand. And when that happens, the material at the edge can start to fall off of the star and onto the neutron star. Looks something like that. Okay. So here we've got a neutron star here at the very center, and this kind of starting to age and expand star dumping the material out onto the neutron star. And then when it happens, it forms this whirlpool of material. Okay. Have you ever gone to the zoo or a museum or something like that, and they've got those little coin drop things that spiral the coin around into the donation bucket in the middle? The same sort of thing happens. Right? You drop the coins in, they spiral around until they finally reach the center, going faster and faster the closer they get to the center. Okay. All that stuff moving faster and faster as it gets to the center, when it lands on the neutron star, it's going pretty fast. It's going faster than the neutron star is spinning. And that spins up the neutron star. Okay. So responsible binaries recycle their old neutron stars. Okay. All that material starts to spin it up faster and faster and faster. So instead of a neutron star spinning every 1 second or every 2 seconds, these will spin hundreds of times every second. So if you can imagine traveling the outer loop of Baltimore hundreds of times in 1 second, you'll get to kind of a feel for how quickly these things are going. Okay. So what's left at the end, eventually this accretion stops, this robbing of material stops, and you're left with this really fast-spinning neutron star at the end, okay, that's spinning up so quickly. This is the kind of thing that you can see now as a pulsar. Okay. So every time these magnetic poles of this spinning neutron star sweep past you, you see a bright flash of radio light. That's what it means to be a pulsar. A millisecond pulsar, okay, or recycled pulsar, is one that has been spun up to these fantastic speeds. And you see a pulse hundreds of times every second. These are known to be gamma-ray emitters. We can identify them out loose in the galaxy. We can see that they're emitting gamma rays. So one hypothesis then for the gamma ray excess in the center of our galaxy is that there's a whole bunch of these really rapidly spinning neutron stars hanging out in the center of the galaxy, each of them emitting gamma rays and blending together just like a pointillist artwork. Okay. So we've got these 2 ideas, right? So there is a hang-up in that we should see some pulsars, right? We can see them in the radio. Why don't we see them in the center of the galaxy if they're there? Why do we miss them? We should actually be able to point a radio telescope at them, right? And see the pulses coming, but we don't. There are some reasons that might happen. There are hot electrons, or just free electrons, in the galaxy loose, and whenever a radio wave passes by those, it slows it down. Okay? And when it slows it down, it smears the radio pulse out. So whereas the radio pulse might start out as this really coherent single thing, at different frequencies, the pulse is being delayed by different amounts. So when you look with a radio telescope, instead of seeing one nice, neat pulse, you're getting a smeared out pulse. And that makes them harder to detect. Inconveniently, this smearing is worse at the center of the galaxy. So if you measure how much smearing there is as a function of the galactic latitude, and how far away from the plane you move, right in the middle of the plane, it's terrible. Right? And out towards the edges, it's fine, and you can see the pulsars no problem. Looking right towards the center, there's all these free electrons, and the pulses just get hopelessly smeared. That's worst at low frequency, which is a problem because pulsars are brightest at low frequency. So if you want to find pulsars, you want to go to really low energy radio, because that's where they're really bright. But that's also where they're smearing the most. And as you move to where the smearing is less severe at high frequencies, then you're running into problems with how bright the pulsar is, and it's just hard to see. So we've got these two scenarios to explain kind of this puzzle. One is that there are particles we can't see, dark matter, and the other is that there are pulsars we can't see. Which one is it? Is it either of them? Is there some way to find out? Well, there are a couple of different ways you could approach it. There are groups out at the Large Hadron Collider in Geneva, in Switzerland, looking for these dark matter particles, looking to see if they can find something that looks like it would be responsible for this excess of gamma rays. I'm not part of that effort, so I'm not going to talk about it anymore. The other way is we could go about looking for new pulsars. See if we can find them where it has been difficult to find them before. And we can take advantage of a couple of things. One, pulsars are small. Right? They fit inside the loop around Baltimore. The other thing we can take advantage of to see if we can find them is that they're bright at low frequencies. We know these two facts about pulsars. So what we can do is go out and look with radio telescopes and see if we can separate things that are small and bright at low frequencies from the rest of the stuff we can see. Some of the rest of the stuff we can see are these massive galaxies shooting out jets of particles from a central source, black hole, gobbling up material as rapidly as it can. These big jets that are large on the sky, they're not small, so we can see them. They are much brighter at low frequencies, but they don't fulfill both requirements. Right? They're bright at low frequencies, but they're not small. That central source is very small, but it's not super bright at low frequencies. Pulsars are much brighter relatively. So by combining these two facts, we can try and separate out the pulsars from kind of distant black holes and other sources that might cause confusion. Okay. So we need lots of radio dishes to make a really high resolution image, to really zoom in on the small things. So this is the VLA, the Very Large Array, out in Socorro, New Mexico. I don't know if anybody's seen the movie Contact. Yeah, it was in the movie Contact. Jodie Foster was out there on a CB radio while she was trying to take radio data. Right? Not a good call. Yeah. So this is an aerial photo of the VLA, just to try and give you a sense of how big it is. You can't really see very well the arms here, so I'll highlight them. This is where all the different antennae can go. They can spread out over 10 miles across. I think 22 kilometers is the length of the arms, maybe 21, if I'm not remembering that right. So your size of the telescope basically becomes the size of these arms when you link them all up. Okay. So using data from the VLA, I got to go out, which was a lot of fun. They let me climb into one of the dishes for some reason. We got to use some data there. They taught me how to use it to look for these compact radio sources. So this is just a small section of one of the images we took with the VLA, looking for small objects that are bright at low frequency and not very bright at high frequency. And you can see that there are these, I've circled some very small point-like objects. And you can also see here something extended. It's clearer on my screen, but this is a supermassive black hole kind of shooting out some jets of material out around it, which is kind of cool to find accidentally, right? Because you're not really looking for those, but it's there and it's neat. Then after we've got all those point sources of small objects, we can look at how bright they are at low frequencies compared to high frequencies. So stuff further down on this plot is bright at low frequencies. stuff around 0 here is about the same brightness at high frequencies as it is at low frequencies. And I've plotted up just 3 different fields of where we observed, 3 different parts of the Milky Way. And we can see that there are several sources here that are points and very bright at low frequencies compared to high frequencies. So we've got all these candidates now, things that look like pulsars. But the smoking gun really is to search these candidates. So these 2 were bright at low frequencies and not at high frequencies. This one was not, so we throw it out. We're not going to look at it anymore. But we can now go and look at these objects with something like the Green Bank Observatory. Okay, this is out in West Virginia, not too far away from here. And we can point this massive dish at each of these candidates and look for pulses. You might say, well, you didn't find pulses earlier. Why would you find pulses now? What's better about having done this? Right? And the thing is, if you look at where these are on the sky, the red dots here, the red circles, are where the pulsar candidates are. The blue circles are the part of the sky that this dish can see. Okay? And you might notice there's a lot of the sky here that we don't have to look at anymore. We can ignore it. That means that we don't have to search for pulsars kind of blindly in the dark. We can direct our search. We don't have to waste the time here, and instead we can put all of that time into the center, or onto the pulsar candidates, trying to build up some signal. Right? Because if you want to find something real, you need enough signal to noise. Okay? So by focusing our pulsar searches, we can find some real pulsars and not have to hamstring ourselves by searching where we know pretty well there aren't any. Okay. So pretty soon, we'll be in a position where we'll have so many pulsars we won't know what to do with them, right? We won't know what to do with them all. Okay. So at that point, I'll go ahead and open it up to questions. So.
All right, questions for... Yes?
Okay, other than just timing it, is there anything they can use the beam for that they emitted? I mean, is it like shadow other objects or something like that?
That question.
Yeah, can we...
I couldn't even hear it myself.
Other than just timing the beam, can they do anything with it, like shadow other objects or?
That's a good question. So in general, sometimes it is neat to be able to see light being emitted from something strongly bounce off another object, nearby structure, and come to you. And that kind of thing has been done with other sorts of objects. I don't think it's ever been done with pulsars. Maybe some of the X-ray pulsars, some of the X-rays could be bounced like that. I'm not aware of that, but it's the kind of thing that someone might already have done and then now fuss at me for not knowing about it. But I'll see.
We have a question way in the back. Gonna make you work, Grant.
Oh, always. Ready?
Oh, good catch.
All right, so I was just wondering if that there were, when I was actually at the Green Bank listening to a lecture there, they talked about a source of radio waves that they didn't know. So you talked about how this could also generate waves in lower frequencies. So I was just wondering if they're sort of the same mystery. They're called fast radio bursts.
Yeah, fast radio bursts are something a little bit different, though they're also something that is not really explained and is really interesting. Fast radio bursts pop off kind of all over the sky. So here we have kind of a sky map of just the Milky Way and everything. If we were to draw a circle around every fast radio burst that has been seen, they'd kind of scatter around, right? They're not coming from just the center of the galaxy here. So it's a good question. And neutron stars probably have something to do with fast radio bursts. They're probably tied because they're happening so quickly. You need a lot of energy on a very small scale for those fast radio bursts. So neutron stars and pulsars more generally, yes, probably are tied into that somehow. Yeah.
Okay, we have a question from online, which is intriguing. I haven't thought about this before. Can one use pulsars for gravitational lensing? And I'm not sure, because that strikes two questions in me. Yeah. The lensing around a pulsar, yeah, but you'd have to have a really fine resolution. But if you can get a pulsar that gets lensed, multiple sources, then you could see the timing difference between the multiple sources. That would be cool.
That would be really cool. Yeah.
So
I'm not aware that that's ever happened, but that's a neat idea. Yeah.
Yeah. Because
so there is a supernova, the kind of thing that makes a pulsar, that was lensed by a distant galaxy. You could see the supernova arrive at different times.
we got to explain, make sure everyone knows gravitational lensing. Okay, do you want to take it?
Sure. Yeah, so gravitational lensing is just when light gets bent by gravity. So if you have a massive object, like a neutron star or another galaxy, as the light is passing by, the gravity curves the space around the object, and that light traveling through that curved space gets bent. So it just acts like a big magnifying glass. The path of the light gets diverted.
Right, and the point I was making is that sometimes the light comes this way around it, and sometimes it goes this way around it, and then sometimes it goes this way, and you can actually see three different paths to the same object. And so if there's a timing event going on here, it can take different amounts of time to pass through these three different curvatures around the object, and then you can tell the timing difference to measure the gravitational lensing that's going on. And as you said, we've done it with a supernova and maybe one or two other things.
Yeah, but I'm kind of wondering if there could be like microlensing of pulsars or something. I mean, that would be pretty rare, I would imagine.
That would be cool. All right. Questions from the live audience? Yes, we do. Go ahead.
So you've left us all hanging because you've gotten only as far as you've gotten. And if you were to get all the data that you wanted and you were going towards your holy grail, what would you ultimately know?
Yeah, so we actually have the data from the Green Bank telescope in hand, and we're working on it now. But we don't have the answers yet. We have found enough candidates to explain the Fermi Gamma-ray excess. It's entirely possible that that all those candidates are not pulsars. So it's too early to say that it's done. But we have found enough small point-like objects with really steep radio spectra that are very bright at low frequencies and not at high frequencies that don't have like counterparts in infrared and other types where you can identify it as something else. So screening out all the contaminants, we're left with enough candidates to explain it. It's still premature to say that it's explained, but I think I am personally optimistic. It's maybe about as far as I can go.
It's a nature of research.
Yeah.
Question. Jocelyn Bell,
Yes.
1967, is credited with discovering pulsars, correct?
Yes.
So
Yeah.
how is it?
I think I had a picture of her pulsar there too. With where was it?
How is it that somebody that could discover something new? She was denied the Nobel Prize, correct?
Yes.
How did that happen? She was a grad student, right?
She was a grad student. Yes.
How did-
and her PhD advisor got the prize.
Yeah. How did that happen?
Yeah. Yeah. So I actually got to meet Jocelyn Burnell when I was at Texas Tech, and Jocelyn Bell Burnell, and she was very easygoing about it. She was not at all bitter or upset about what had happened, even though I think she might have every right to be. But her attitude was that it was not traditional for graduate students to receive the prize. Personally, I think it would have been fine to give it to her, but she was the one who first, identified it. Her PhD advisor also did a lot of work on the object, so I'm not trying to say that he didn't deserve the Nobel Prize as well, but I think it would have been, I agree it would have been good to include her, that I think she personally, I would say that she deserved it. But yeah,
Her picture is on the poster out in the hall.
it is.
One of the great women in.
It is. You know, she made an enormous contribution. That discovery of hers, this object, in fact, of the regular pulses arriving every once a second or so, birthed a whole new field of astronomy. And it was something that we didn't. Right. Yeah. Exactly. And so it's not every day that someone births an entirely new field of study in the natural sciences. Right. So yeah, I think it would have. You know, it merited. It clearly did merit a Nobel Prize because they awarded one for the discovery. Yeah, I agree with you.
For the online audience, it was referenced that we have a picture of Jocelyn hanging here at the Space Telescope Institute.
Yeah.
All right, other questions? Going once, going twice. All right, and Irini arrives right on time. Okay. Ladies and gentlemen, that is Irini Lambrides, and she will be taking people across the street to the Maryland Space Grant Observatory. Where would you like to hang out? You want to hang out over here by the door? Okay, so if you would like to use the telescopes across the street, please join Irini over here. Next month, the art and science of astronomical image processing. Please join us. And let us give one more big hand for Dr. Christopher Britt.